So, good afternoon everybody. Thanks to Ralph and Gus for the invite to present to, which is always something organised by Ralph. It's always a very interesting mix of people, so we always appreciate the invite to come along. So I'm going to give you an overview on where things are going on the satellite Earth observation domain for maritime knowledge. And I'm going to be talking to you about satellites to start with, but not just the satellite instruments, also the evolution that's taking place in the analysis tools that we're putting in place, and eventually how things are moving forward with AI, big data, and on the space side, quantum sensing as well. So we're very complementary. So firstly, from ESA, in terms of Earth observation, we have developed and we've put in place a number of satellites really that are responding to a range of environmental priorities. These are defined by policy requirements, things like the European Union, so common agricultural policy, maritime strategy, these sorts of policies defining the environmental parameters that want to be characterised. The IPCC defining essential climate variables, the sort of things that need to be measured, as well as we have regular structured scientific consultations that agree every 5 years or so an Earth science strategy and the observations we should be collecting for that. And these include a large number of ocean or ocean-related sensors. Over the last 15 years and going forward over the next 15-20 years, in Europe and within ESA, we're putting a lot of satellites into orbit, providing a whole range of data sets. We structure these as scientific, Copernicus or operational data sets, and meteorological data sets. I think in the scientific ones, so these are really individual standalone satellites that are addressing a combination of significant gaps in our scientific understanding of Earth system processes, as well as using a leading-edge, high-risk technology to provide some sort of measurement addressing that knowledge gap. So, for example, we have one satellite up there called GHOST or GOCHI, depending on which part of Europe you're from. That's measuring very, very, very precise gravity anomalies, and the high-risk technology there is it's very, very accurate accelerometers. To give you an idea of how accurate the accelerometer is, or the 6 accelerometers, it is supposed to, now we haven't tried this in practice, but extrapolating from the numbers, apparently it could measure the equivalent of a snowflake, or the impact on an oil tanker of a snowflake landing on it. Okay, so that's the level of precision that the thing that you see that turns the screen in your mobile phone. When you turn your screen, it turns the picture. Very, very precise version of that we've been using to measure gravity anomalies. So we've got a number of, so that's been providing geoid and things, we provide soil, ocean salinity, etc., scientific activities. Copernicus is an operational evolution of what we've been doing since the early 90s. So these are instruments that really address operational observing gaps. And these are, from the ESA side, fairly bog standard instruments, and then leave space for other guys to do more complicated things. So we're looking at technologies such as imaging radar, C-band imaging radar for things like maritime surveillance, marine pollution control, optical multispectral infrared mainly for land, but because we, due to the combination of requirements, it had to be quite high performance, so it turns out that's quite an effective maritime monitoring instrument as well. And then the standard oceanographic measurements, ocean colour, sea surface temperature, etc. I include the meteorology systems there as well, because increasingly, and also when we get into the AI capabilities, systems that were designed for meteorology that are measuring large-scale parameters, when we put these together with the other data we have, and when we start applying techniques such as super resolution, these can be actually increasingly useful for providing oceanographic information as well. So although, for example, Meteosat's second generation is providing low resolution land or sea surface temperature, it's providing it every 15 minutes. Okay? Now it is at a resolution of somewhere between 2 and 4 kilometres, so it's fairly low resolution. But once we start combining it with other data and applying AI, things like super resolution, I mean, we're looking at something like 1 kilometre every 15 minutes, and with the next generation of meteorological missions becoming available from 2021, 2022, this will be a game changer for characterising ocean and coastal processes as well. So just in terms of Copernicus, this is the situation that we're in today. So imaging radar, we've got 2 satellites in place. We're building 2 more, and we've got funding for a whole bunch of various others. So that basically guarantees availability of imaging routes of C-band imaging radar until about 2030. Again, Sentinel-2, optical and near-infrared, that's guaranteed over the same period. We've got 2 satellites there, 2 oceanographic satellites. This is a game changer in terms of this isn't just a one-off mission. These data will be available. They have been available now. They are designed as continuations from previous observations going back to the early 1990s, and they will go forward until, well, they're guaranteed until the 2030s. So this is a very, very long time series. You can start really relying on this availability for your operational monitoring systems, as well as the performance that we're getting. So for example, Sentinel-2, that's just showing a cloud-free mosaic of Africa, the Africa picture there. Sentinel-2, the optical and infrared system, that gives us, at 10 metre resolution, the entire land and coastal area of the Earth every 5 days. I mean, we're talking about having too much data. I mean, we're throwing even more data at you. I mean, we've already got way too much data. We're getting 10 metre resolution of the entire land and coastal area every 5 days. Really lets us start looking at not just, for example, source and sink change in some of the global biogeochemical variables, but also start characterising some of the exchange pathways as well. Similarly, we get a radar image over an area every 6 days to the orbits. And again, this type of repeat is really opening up new capabilities. In terms of the quality of the observations as well, like I said, I mean, Sentinel-2, or that's the one on your left. It wasn't designed as a oceanographic mission at all. It was designed to do agriculture and forestry and things, but it turns out we can do 10 metre resolution lets us characterise a lot of vessel parameters in terms of colour and things. It lets us have a lot of high resolution interaction between the ocean biology and the physical oceanography, so things like compression of algae with internal wave properties. And once we start combining that, the 10 metre resolution from the Sentinel-2 with the 300 metre resolution of the Sentinel-3, for example, on this, that sort of combination lets us go from open ocean marine biogeochemistry into the coastal area as well, really enhancing our knowledge of a lot of the fine scale processes that we could infer but weren't directly observable from previous satellites. Not content with that, we've been working with Member States and European Commission to address a whole bunch of observation gaps in the Copernicus programme. So some of these I was going to say you won't care about them, you will care about them, but they're not immediately relevant to oceanography. So I mean, top priority is have some sort of high resolution CO2 imaging spectrometer, so we can start really looking at local image, rather than just characterising the state of the atmosphere and saying, oh yeah, there's a bit of CO2 over there, and that's not very happy. We can start actually characterising where the CO2 is coming from and really start looking at emissions. Given that's a top priority of the European Commission, we're basically build it or else, so we're building it. We're building some other ones as well that will be of direct interest to the maritime community. So for example, the one at the bottom left there, sea ice concentration and sea surface temperature, that's a passive microwave imaging thing that will let us do a lot of other things as well. Hopefully passive microwave is pretty cool. We'll have L-band SAR, L-band synthetic aperture radar, so although that is designed as a vegetation parameter retrieval system, L-band SAR over the ocean lets us see a lot of things that are a bit more difficult to see with the sort of imaging radars we've got just now that are higher frequency. And the food security mission there is a hyperspectral imager. So again, somebody mentioned NASA were saying we can measure variations in oxygen concentration on Mars. We've had a hyperspectral imager around Mars for the last 10 years at least. We've never been able to have one around the Earth on a sustained basis. I mean, been various short-lived attempts. So this will be something guaranteed for the next few years. And again, that lets us look at ocean biology in a new way. In terms of the science, rather than the more operational, as I said, I mentioned GOES or GOCHASE. MOS is still operating, so we're measuring ocean salinity amongst other parameters. Cryosat as well as being an altimeter, letting us retrieve ocean currents. It's also giving us fairly unique characterization of ice characteristics. And we're launching some other ones as well. So we're launching biomass, which is a very long wavelength synthetic aperture radar, which will give us some interesting observations over the marine and coastal areas as well. And FLEX, which is a fluorescence mission, which will hopefully let us see some interesting things in coastal areas as well. And it's not just us, there's national missions. So the Italians have launched Prisma and a hyperspectral that will hopefully lead into the Copernicus system. Germany will be launching another hyperspectral imager called EnMAP. We've got constellations. Let's say we've got meteorological systems that are increasingly performant and increasingly relevant, not just for meteorology, but for, I would say, whole water cycle characterization as well as ocean dynamics. And we have cooperation with a whole bunch of different satellite operators. I can't remember how many there are. They're all listed there. So all of these satellites are providing data that are available to you. Okay, and if you contact us, these data are available to you free of charge. Okay, so that is, I challenge you to find a parameter we can measure from space that you can't get from one of these satellites. Not content with that, and I think also as part of a sort of from the public sector trying to encourage a more systematic development of the European industrial capabilities, we're also working increasingly with the small satellite guys. So commercial guys, they've got a business plan, they get investment to build satellites to do for a particular commercial objective, and we're saying, look, these data is not just for your commercial objective, which is normally precision agriculture for some reason, but if you're measuring that, you can do a whole bunch of other things as well. So there's ICEYE, which is an X-band SAR. The interesting thing about the small satellites in imaging radar, one of the problems we have with imaging radar is due to the trade-off of orbit characteristics. An imaging radar passes over a given area of interest, usually between about 3 and 6 in the morning and 3 and 6 in the afternoon. So if you're a bad guy and you want to go out doing something bad, you're just going to work in the morning, come out at lunchtime, do bad things, go back, and we can't see you. There's no satellites going over at that time. Okay, so hopefully with these small satellites we can have a bit more of a dispersed orbit and a bit more persistence over these areas. And then there's new technologies as well. So we've got imaging, satellite video becoming available. So EarthEye launched one. It doesn't work anymore, but they're launching some others. There'll be a Slovenian satellite video as well. It's only 2 or 3 minutes of video per orbit. So everybody says, "Oh, that's rubbish. We want total CCTV," but it's not rubbish. It's movement information. And when you put the movement, even 2 or 3 minutes of movement, together with all of the other information you have, you can start looking at things like what's the behaviour of top of food chain predators, or which direction is a boat moving in. So that sort of information, put together with other information, really is unique and saves you a lot of time and gives you insight that would be difficult to get in any other way. This is really, there's a lot of investment going into a lot of these small private sector guys, and the large majority of these things are addressing Earth observation parameters. So the small satellite capability, both for Earth observation, but also for a whole bunch of other things like transponder detection and passive radar detection, things like that. There's a whole bunch of things coming in there from the small satellites, and that's leading to an increasingly crowded space over the next few years. And it's not just the instruments at this point, we're also looking at things like IoT technologies, also enabling us to combine with things like high-altitude platforms and drones and things. So we've got a whole bunch of complementary data sets that will all be connected up and providing really this range of parameters, a lot of which are either directly oceanographic or of interest to the maritime community. We realise that's a lot of data, and it's not always easy to get your hands on the data you want. So we're also putting in place tools to help. So it's not just like we do satellite altimetry and we retrieve the ocean currents, and then that ocean current is assimilated into a model. And we're making available tools now that take the difficulty out of getting your hands on the satellite data. I remember we're talking to the lady who used to be General Secretary of HELCOM, and she said, "Oh, Earth observation, yeah. We were thinking of Earth observation, and we had a look, and we realised we had to go to this FTP site, and there was all these files, and they've all got really long names. Okay, so we couldn't remember which one we wanted, and they're all really big, so it took us ages to download them, and then we had to buy this expensive software to visualise the data, and we realised we got the wrong image. So we had to go back, and so we don't want it anymore. We're just going to use our boy data." Okay, and it's a fair point. Okay, so unless we as the space community come along and make it easy for the non-space guys to access the Earth observation data and integrate it into how things are being done, then a lot of this investment really is for nothing. So we're putting tools like this in place. This is our Ocean Virtual Laboratory. I'll come back to some other things in a couple of minutes, but this is there really to make the whole thing banal. All right, you don't have to be a clever data scientist to get Earth observation data anymore. If you are a clever data scientist, then that's good, but you don't have to be, and it should be much easier. So just sort of 2 minutes just on some of the things that we can do with these data. So GOES or GOCHIG give us very, very precise geoid. It's the basis of all your, as well as being the basis of a lot of ocean current characterization, it's the basis of all your location-based services in your mobile phones. But I mean, this is a point I'd like to make as well. What we do for oceanography, okay, it's a sort of multi-sector investment. Things we do for, like say, things we do for agriculture have impact for oceanography. Things we do for oceanography have impact in other areas. So measuring the gravity anomaly, primarily for ocean circulation, it lets us do other things. It lets us, basically combining lots of different gravity anomaly data, it lets us characterize the build-up of mass in subducting plates. So we're not doing earthquake prediction, but we can start characterizing the dynamics associated with that, or build-up and loss of groundwater. We can start looking at issues preceding onset of drought. The other thing we detected was the top of the atmosphere shock of the earthquake that was in Japan, which we didn't expect to do. SMOS, or soil moisture and ocean salinity. So it was, as the name suggests, designed to measure ocean salinity, so we can characterize various unknowns such as freshwater influx into the Atlantic. That's this part here. But also by better processing of the microwave data, we also start characterizing alkalinity as well. So this lets us look at parameters that really the satellite wasn't designed for. And when we put it together with Cryosat, we're able to measure the entire spectrum of ice concentration, both from very, very low concentrations that would show up as in the imaging microwave, and then the higher concentration show up in the synthetic aperture altimeter. We can do sea ice, well, yeah. We can do maritime surveillance, pollution control. This is an example from, so this was part of the Clean Sea Net service from EMSA. They said, oh look, there's an oil slick there, this is Ireland at the top. And the Irish Coast Guard said, right, that's an oil slick. And then they phoned us up and said, what are these two other things? And we said, well, they're oil slicks too. And we said, and that's a boat. And all these oil slicks look like somebody's been trying to do an at-sea refueling in your coastal waters, and they've had problems doing it. So they sent out an airplane, and they saw this, okay. And sure enough, there's these boats in the corner, and then they had a look at the boat, and it's our favourite Russian aircraft carrier, and it's refueling ship. So they were called up by the Irish Coast Guard and told to get lost, and told to pay for the clean-up. So you know that type of analysis is not just routine detection. We can actually do fairly sophisticated things. We can do fisheries. We're working with not just in Europe but also developing countries. We're working with the World Bank in West Africa Regional Fisheries Programme, for example, or Southwest Indian Fisheries, SWEO, Southwest Indian Ocean Fisheries. So basically supporting countries that don't have their own capability to manage the fishing resources, this type of capability, because we have so many conflicting requirements for satellite data in Europe to observe European capability. It actually costs us nothing to observe outside of Europe. Okay, the capability to observe the entire Earth's surface every 5 days comes actually as, we didn't design the system as that, we didn't say that's a requirement, we say we have to be able to measure particular fields in horrible places like Scotland or Ireland, which is always cloudy, and in order to guarantee an acquisition at a certain point of the growing season, the trade-off of that is that we need to be able to basically cover the entire surface every 5 days. So we can do maritime surveillance for West African countries, detect illegal fishing, transfer at sea, everything, but really at no cost, or no effective cost. So we're really trying to get European technology into developing countries as well. And we're supporting other blue economy developments that are part of World Bank investment as well. So, for example, one of the big issues we have again in West Africa, also in other areas, is coastal erosion. In some places, it's natural coastal erosion. In this part of West Africa, it's actually people are driving onto the beach with lorries, digging the sand and taking it away for construction. So we can monitor the lorries as well. We can, we're mapping benthic habitats, both coral reefs and seagrass. We're measuring bathymetry, not to IHO standards, but is good enough that you can understand what's going on. And we're doing the normal things like water quality, sediment transport management as well. So again, that lets us do some analysis, such as there was a problem in Tuvalu. Tuvalu used to have a very nice coral reef, and they had nice fish, and everybody ate the fish, and everybody was happy. And some people started growing pigs, or raising pigs, and after a while, the coral reef was covered in a certain type of algae, and the fish that they wanted to eat went somewhere else. And some other fish that came along, let's grow more pigs. Okay, so there's a big problem, and the World Bank said, hang on, what's going on here? You're not doing sustainable development. You have to be doing all this sustainably. And they said, oh no, it's climate change. Okay, because of climate change, then we're getting this algae, and it's not us. And so we did this analysis with CLS, I think it was. So we basically took the 20 years of the essential climate variables of all the oceanographic data. That's the sea surface temperature and the ocean colour you can see flashing around there. And we said, basically, look, there's absolutely no correlation between algae growing events and anything that's happening in the ocean roundabout. This isn't anything to do with climate change. It's to do with runoff from the pig farms, the nutrients from that, encouraging the growth of the algae, whatever. So, but that type of putting everything together is only possible when you've got a critical mass of Earth observation data that enables that type of analysis. Similarly, yeah, so we've got this, we can do other things like wave resource characterization for offshore energy. One of the fastest things to go commercial, I mean, the oil and gas guys knew about it ever since synthetic capture radar it used to be, when it stopped being a secret technology, for secret slit mapping for new basin characterization. And also, like I said, the data are systematically used as for generating essential climate variables. When you look at, how much satellite data was in the latest IPCC report, it was absolutely massive. So there's a whole bunch of things happening. There's commercial services starting. A large part of that are oceanographic, mainly maritime surveillance. There's a whole ecosystem of different people starting to provide services in different ways, from single satellite providers providing dedicated analytics to a whole ecosystem of people all doing slightly different things. And that's where we are now. If you think about it, there's a whole bunch of new technologies coming along that are really going to be changing how satellite data are used and how satellite data are combined with some of the stuff that, for example, Terry was showing before. So things like blockchain, visualization technologies, AI, and big data. I'll just talk just for 2 minutes on AI and big data. In terms of AI, isn't just automatic detection of airplanes or dogs and cats or whatever in pictures. There's a whole bunch of things that AI can do. The integration of supporting a more effective integration in data fusion, image recognition, other processing such as super resolution, all of that can be enabled by AI. So we're looking at a number of different challenges in there. How do we really get the best out of the Earth observation? Because where we are now, I was thinking, Terry was saying, do we have too much data? We have so much satellite imagery now that in the world, there are not enough human eyes to look at all the satellite images we've collected. Okay, so the only hope we have is to have some sort of AI-based processing of these data and big data analytics to combine them into something useful. For example, how can we useful things would be things like hybrid data analytics. How do we combine for complex processes? So for example, some of the exchange processes in biogeochemical cycles, where that exchange process is quite complicated and we can only model part of it, the other part of it we can use data-driven or AI-based characterizations, rather than, it might look a bit different, but it's still the overall end-to-end characterization it lets us get a handle on something that we wouldn't otherwise be able to do. Okay, so AI really can, it helps us do the analytics, it helps us combine the Earth observation with all these other data sets. Hopefully, I mean, this is where we're looking for now. So can we go beyond how we're actually analysing things and start getting a bit more sophisticated? So for example, how can we combine different oceanographic data from Earth observation with, for example, acoustic data, underwater acoustic data of different mammals or fish or whatever. And when we're doing that, then it's going to have to be big data analytics. Last minute, I'd just like to say how that combination will have to be, it is enabled by what we're calling an exploitation platform. So again, this type of technology means you don't have to go off to obscure websites and download data. All of this is taken care for you just from a website, a single interface into this platform. It also lets you upload your own in situ data or access other people's in situ data. It's enabled by this sort of capability, but you don't need to worry about it. You have this sort of central thing that enables access to all of these other data sets. The other spin-off we have is because as part of this enabling, we are generating a whole bunch of analysis-ready data sets or data cubes for Earth observation. The technology to do that also lets you put your other data into a data cube structure as well. So you don't need to go off and do something. You can just use our data cube, or it's not even our data cube, the software. If we're doing the data cube, you can use that. Processing is there. I won't go into these other things because it's run out of time. Just take home messages are there. So thank you. Sorry for going on a bit. Hope you enjoyed that.